Dean R&D. He has served as scientist at CSIR, CECRI. He has granted, he is having 7 patents into his account and has developed 2 technologies, which is currently being used in construction sector in India and in CPCC technology. He has several publications to his credit, and he is interested, very much interested in motivating young minds for innovation. And he is also a coordinator for NI LabVIEW Academy. With this introduction, I would like to hand over the session to Dr. Kumar sir. So Kumar sir, over to you, sir.
Okay, thank you, Mr. Ram Babu. Yeah, I think participants they know me very well already. I have been in one of the session. Now it is the next 2 sessions I am going to take up. So in that we are going to discuss, I think mostly on the applied aspects. Here, our NI tools, how we have used for making vibration analysis and as well as the condition assessment, like that the things are going. In the first session, I will be discussing about the vibration analysis on the structures. So vibration analysis we can do either in the structures, either steel or concrete, or otherwise in the girders, or otherwise in the motors, or in the equipments. All those things we can make vibration analysis. Suppose even in the aircraft engine, we can make vibration analysis. Now it is badly needed for DRDO. I think vibration analysis test is going on. If anybody knows about that, they can take up the projects and they will easily sanction some good projects, and you can get a project from the DRDO and you can pursue that. So this is vibration analysis is one of the very interesting and important one. So today I am going to share my screen now. First I am going to talk about in the PPT form what are the vibration analysis we have done, and after that I will be showing the real time. Real time means simulated type I will be showing you. So right now I'll be sharing my PPT. My screen is visible, Ram Babu?
Yes, sir.
Yeah, okay, thank you so much. So today I'm going to talk about all vibration related matters, especially in the structures. For example, these are the 4 different vibration analysis I'm going to explain today. Number 1 is building vibration observed by the occupant. So I will, when it is coming, I will explain in detail. Next is due to vibration, longitudinal cracks were observed, and the checking the cable vibration and the checking the bearings. So these are the 4 different important points which we have already done in Bangalore. So now this is the building vibration. What happened in Marthagalli Road, one of the tall building, during the time of the flyover construction, they have used the rammers and also they have used the digging tools. So there are heavy earth movers they have used. Because of that, the vibration on the adjacent building, it is observed by the occupant. So there are some vibrations in the entire building in a different floors. Especially in some locations, they found the vibrations. In the building, there are some cantilever type of portion available. In those portion, it has got high vibration. The reason is the vibration is in the vertical mode, they got the vibration. If it is a horizontal mode, that is very, very dangerous. Normally in the seismic, it will be on horizontal modes. So now here the occupants, they observe the vibration on vertical mode. Because of the vertical mode, they observed in the cantilever portion more. Because the cantilever portion sways are more. Now they there's an international IT company, and they referred, they have informed to the building owner and in turn the building owner, they came to us. The company is multinational company, and we have made a vibration analysis for continuous 24 hours. Especially now you are seeing the first figure. There is an accelerometer we have connected with on the floor. It is at the free end. Here the vibration accelerometer is connected to the MyRio. I have used the MyRio. The MyRio is also having high updation rate, and that is connected to this the middle one that is in the laptop. So 24 hours we have seen what is the vibration is going on and all. For that, our entire student team, they were present there. 24 hours our students were there and they have monitored. After acquiring of the data, then we have made complete assessment. So now the next forthcoming slides I want to tell you. In this last photographs, my UG team and our director and myself, we are making the vibration analysis. So after 24 hours, we have found that this is the frequency, and with respect to time, 24 hours, every 15 minutes, we have logged the frequency. The vibration, real-time vibration is measured. After that, the data is acquired, and that data is subjected for the FFT analysis. Then after that, it is segregated as a fundamental frequency. So the fundamental frequency is every 15 minutes we have observed. For all the 24 hours, we have logged the that is frequency analysis. You are seeing that with respect to 24 hours, we have got there are vibration fundamental frequency ranges. The frequency, it is starts roughly in 1 and it is with 1.5 Hz. But in building, if suppose the lower frequency observed less than 1, that is dangerous. That means if the lower frequency makes the building more oscillation, that means more deflection. It may be greater than the allowable limit of the deflection. In that case, the building is subject to crack and failures and so on. We have found almost all the frequencies that were 1.1, more than 1.1. Very few, only 2 we have got less than 1, but that is we can neglect it. So with this, the analysis rate, analysis we have given to the concerned company people, those who are sitting in the US, and our report is very well taken, and finally they got cleared. Okay, nothing to worry about like that. So I'll be showing some reports on that. Yeah, these are the reports. I think I don't want to show exactly whom we have done and all. These are the orders. And so what are the methodology measurement methods we have used? Here you are seeing that we have used the triaxial accelerometer, and that was affixed on the floor. The signals were captured on 3 axes using the NA-MyRio. LabVIEW 2017 we have used for making a coding, for capturing the signal and as well as for the analysis. Then the captured signals were analyzed by FFT and the frequency was recorded. So the recorded frequency in a different span were presented, and finally for the 24 hours the analysis report has been submitted. So when you are seeing that, this is our photographs. Yeah, this is the generally the perceptibility of vibrations threshold for is a direction. So this is acceleration versus frequency we have to make. So in that it has to go like this. Suppose if it is deviating from this line, there will be a difference. For example, there will be a problem in health of the structure. Here we have seen this is the acceleration versus frequency. This is within the limit. That is within the limit. You can see here, this is the one. 0.00 and below, it is in the horizontal mode. Whatever be the frequency, we have got in horizontal mode. You can see that frequency also between, this is 2, this is 1, 1 to 2 is the horizontal mode. Right? This is a horizontal mode. So our frequency also maximum 1 to 2. So now whatever we have got, it is in a horizontal mode. So this also satisfies. So the frequency shall be greater than 1. Then acceleration also we have got this. Next, the vibration measurement, the frequency is with respect to time. This is measured, and this also proves that the frequency is greater than 1, and also all along it is uniform. So need not to worry about it. So 24 hours why we took is, suppose if any ramming is happening in between, then that vibration may affect the building during that time, if any peaks, if you are observing or not. For that purpose, we have made for 24 hours. But all the 24 hours, we come to understand that it is almost may not be much problem. And finally, we have concluded and we have submitted the report. So that has shown that, yeah, we can really do vibration analysis for any structures and buildings and machines. So this is the one we have done for one particular tall building. Next one. There is a building due to vibration, okay. There is a building due to vibration. The face wall, it is almost cracked and it is the verge of collapsing. This also very tall building. It's around 22 floors. You are seeing that this is the face wall. This is the perpendicular wall in which it is joined. Yeah, huge cracks from the bottom to top. We have seen the crack. This is the plan of the portion. Actually, the encircled one is the face wall. The face wall is connected to the vertical wall. It is like that. And the face wall is like. So perpendicular to that, they have the wall and it is constructed like that. Now that also addressed to us, and we have used vibration analysis, and after that we have found what is the cause of the cracking, and we have given remedial measures also, what to do and all, everything we have given, and they have rehabilitated. Now there is no problem of vibration over there. You see that the close-up view, this is the plan we have made. The location 1 and location 2. Location 2 is in the opposite side. This is location 1. We have a directly diagonal, and we have a vertical wall and as well as the horizontal wall. So this is the close-up view. The bottommost, they have got less crack, and when it goes up, you just see that even 3 centimeter crack width happened. Because it is acting like a cantilever, and because of the vibration, this has got this kind of thing. Then what is the solution? So we have made all along this, both the walls here and as well as here. The parallel to that, we have placed the accelerometer in every 1 meter interval. And simultaneously, both the accelerometer, we have measured the acceleration. That means the voltage response. That with respect to time, the voltage response is acquired. And after that, that is converted into FFT analysis. Through that, we have found what are the frequency. what are the frequency. Okay, this is the way we have done that job. You see that the with respect to crack width and height of the wall, we have got this is the linear. That means the higher the height, then higher the crack width. Okay, so this is the one we have found with respect to height and the crack width. Crack width is in some places it is 8 m. So like that the cracks have been seen. Okay, now how we solve the same thing. The how method of measurements we have made. We have used the triaxial accelerometer and affixed on both the concrete walls in location 1 and as well as the location 2. And acceleration is measured with respect to the DG set on and off also. In the top floor, there are other machineries were there, the cooling machineries. For example, the entire building is air conditioned. For that, there will be motors which are using for coolings, that is compressors and so on. And also the water pump, the water tank is there. There's the water pumps and all. It is placed on the terrace. From well, it is taken up and it is distributed through pressure. That were also, it is laid on the top floor. So we have used triaxial accelerometer there in both the parallel walls. We have kept it, and this is the way we have made. Here again we have used the embryo for data acquiring. When the data acquired through the MyRio and also fast updating rate it has. So based on that, we could able to have a perfect acceleration values. The waves. Again, 2017 LabVIEW we have used. And again, FFT analysis. The measurements were made during DG off and DG on condition. This is the way we have done. Okay. Now this is the figure I have shown. The middle figure, we have used our laptop at the site, and there our MTech and UG students were there, and is the client, is the general manager, and that particular location we have done, and we recorded the fundamental frequency and its amplitude. Here I want to tell you one thing. First, we thought of that the acceleration we can measure both the walls, and the acceleration may differ from both the things. So if that is there, then what kind of acceleration, where it is differ, and all we can think of. Suppose if the acceleration is different, that is really dangerous. The thing is, both the walls have been separated. That is why the acceleration is different. Like that, we can keep it. So what we have done then, after completion of the acceleration measurement, we have got so much doubt because both the walls are showing the same concurrent frequency. Even after FFT analysis, both the accelerometer and all the three axes shown the same, ditto. We have not got any difference in the frequency. Frequencies are same. Then we are not able to come to the conclusion. Then what we have thought of, again, we have taken the waves. What is the amplitude? In the amplitude, we found the difference. For example, in location 1, location 2, the amplitude is given here. With different distances, different this thing, that is amplitude in volts we have given. So the difference we are able to understand. The accelerometer in terms of volts mean that is corresponding to, that is the G, acceleration. So, and that cases is the physical movement of the particular location. When you are talking about the location 1, the blue is face wall, which is joining on the vertical wall. And the vertical wall, that is in orange color. In location 1, okay, in location 1, when you are seeing here, okay, this is location 1 corresponding diagram also here. You see that this is where you are seeing that accelerometer fixed, that is the face wall. The opposite side here also it is fixed, that is the vertical wall. Now the amplitude, we have found the difference. For example, at 0 meter and correspondingly up to 3 meter, we have found the differences in the amplitude. We have found differences in the amplitude. That means we took only one axis, that is in x-axis. In the x-axis, so the whole joint, it has to move on this direction. For example, the face wall, it is moving very less. That is why the amplitude is less, blue color. Here, this wall, it is moving like this, perpendicular to that. So the movement is more on this. So that is the higher amplitude. Same frequency, but both are in different amplitude. Then what happens automatically? There will be creation of the shear in the exactly at the junction of the joint. Because of the shear, depends upon the magnitude, what is happened? The crack has occurred. You can ask a question at the top why it is both the things are same. Because both are separated. Both are separated, they have got the same amplitude. So the same thing you can see in the others also. This is location 1 and location 2. Then next thing we thought of that, because of the DG set nearby that is created a vibration. So now we have compared location 2. So with DG, then DG set off. Again also we could able to see that the same trend. That means the DG set is not having any influence because that is completely separated. The DG set is kept in the basement and only the exhaust it is came to the top floor, and we thought that that particular thing it is creating vibration. Then we come to understand finally the vibration is due to the machinery which are erected on the terrace. Then we inspected all the machinery. We found that quite a lot of vibrations in the machineries. So the proper padding arrangement, that is damping arrangement, is not given. We recommended all the machineries which are installed at the top floor, that is in the terrace, so is to be properly damped by some damping pads. They have done that job. Next, this face wall, the intersection, we have told them a flexible grout is to be added, even though if any vibration is happened, that will be dampen the section. This is number 1. Number 2, in that face wall, we have given separate anchorage arrangements such a way that even if anything happened, the face wall should not get collapsed. So that design also we have given. So this is the learning from failures. We have got the vibration analysis. We have very well used using the LabVIEW, and we have completed that job. So the next one I wanted to go for. This is one of the very interesting one, which is in Kerpuram Cable Stay Bridge. In the Kerpuram Cable Stay Bridge, the Southwestern Railway, they approached us to check up all the cables. So we checked all the cables by using the same triaxial accelerometer, using the same setup, but it is in the mobile. So my team students are there and they are in the work. You are seeing the right side, the accelerometers are properly affixed over there, and it is connected to that is my Rio that was staged in my car dicky. So from that, there we have UPS, everything, and we have found the vibrations. So the vibration analysis has been done there. You are seeing that this is the bridge end. There is anchorage wires are ending in here, and the entire cable stay bridge is resting on the bearing. This is the bearing. This I will explain you later. So in the bridges, these are the cable locations. This is one is Bangalore side, another is Madras. That means Chennai road. This is the Kerprom road. So in the Bangalore side and Madras side. So these are the cables. It starts from A, B, C, D, E, F, G, H, and M, N. Finally, at the end, we have another 6 cables. So 4 plus 6, 10, the same way 4 plus 6, 10. Both sides 10, 10 cables. But only thing, the span is different. For example, first 4 cables, the same span. And it is made some eccentric. And they equalized with additional cables over there. Now all the cables we have checked it. All the cables, the vibration analysis has been done. So you are seeing here there is a vibration analysis we have done. So these are the FFT analysis on the vibration graph. This is the fast Fourier transform we have made. Based on that, we have made the fundamental frequency. So here you are seeing that the maximum amplitude, which is the responsible for the fundamental frequency, then that we have noted and we have submitted the report. So here we found one of the cable, it has got less than 1 hertz. When it is less than 1 hertz, you can just have in the structural dynamics. So if the more the frequency, it may be taking more load. So you may be having a formula, the cable force. The cable force, which is 2F L, 2FL divided by N and multiplied by mu. This is based on the simple harmonic equation formula. 2F, 2 is the number, F is the fundamental frequency, L is the length of the cable. And divided by N. N is the oscillation, which mode of oscillation. And mu is the density per meter length. So this formula we have used and we have found the force in each cable. So the numerator is F is coming, that is the fundamental frequency. And the numerator we have a mode, either 1 or 2 or something. But generally speaking, we have seen all the vibrations we have found is mode number 1. But the frequency is varied in each cables. There are cables higher frequency means the higher load taken. In one of the cable, it is got less than 1 frequency and correspondingly the amplitude also more and it shows this less load taken. The adjacent 2 cables we have analyzed, adjacent 2 cables are taken very high frequency than other cables and that means that has taken more load. So that particular cable we have noted down and we have given intimation to that Southwestern Railway and they have checked a particular cable, that means the end anchorages it is loosened. And they have corrected it. After that, everything was again we checked, all the frequencies were good, almost in the same range. This is very, very important. At least once in a year, the frequency measurement is to be done, especially in cable stayed bridge. Yeah, this is the one we have done for the Kerprom cable stayed bridge. Then one more thing I want to tell you. Okay, one more thing I want to tell you. The next work which we have done is, next work we have done is the bearings. Checking the bearings. We have at the edge, this is at the Madras side, that means when the Kerprom, it is coming to Bangalore city one side, from the Bangalore city to Chennai road, I mean the Kolar road, that side. We used to say that Madras. So the Madras road. So that side the bearing was there. In the bearing that side there is the six. Four cables they laid out at the concentrated there. So now what happened? Here the bearings. This is bearing number 1 and bearing number 2. We have both the bearings. We have tested the bearing. What happened? Before that, I will make one small. I'm giving you a small video. You can just observe that video. Yeah, this is our team and our faculty members. Exactly on the bearing. Yeah, that is again, we have used the MI Rio and LabVIEW 2017. The accelerometer is connected there. Accelerometer connected on the bearing. The bearing, it is having a two parts, lower part and upper part. The upper part is from the girder. This is the bearing. The upper plate and lower plate. There are two parts. So the bearing is a movable one. Okay. So here what happened? We have to make the vibration measurements both in the bottom and as well as in the top. That we have done. Suppose if the bearing is in good condition, both the vibrations, okay, both the vibrations, okay, it may not be a problem. It will be almost the same. Suppose, for example, okay, the vibration movements and all, if it is different, it is also okay. But if the bearing is not good, what will happen? The bearing is not good means then there will be a difference of vibrations we can observe. You can see here. So bearing 1 and bearing 2. So this is again the same thing. This is in the metaside that I told you. So this is again the same thing. In the metaside we have a bearing 1 and bearing 2. So this bearing 1 and bearing 2 and we have tested here. That particular FFT analysis of the fundamental frequency in X, Y, Z directions we have given. So you see here in the bearing 1, all the frequencies are same, almost same. 1.41, 1.4, 1.72, 1.73, 1.79, 1.79. That means it is both the frequencies are same. That means this bearing is working good. But here in this bearing, you can see here there are difference of fundamental frequency. Here the frequency is different. For example, first one in one axis, you see that 2.09 at one of the axis. And correspondingly there it is 1.40. Here another two things are almost same. So one particular axis, that is in the x-axis, the frequency is differing. That means there will be a problem in that particular bearing. So that is the one also we have explained to the report we have mentioned, and we have given the report to the Southwestern Railway, and correspondingly they have made the how we have to rectify, we have to remove the bearing and we have to clean it and properly lubricate it, again we have to fit it. So that is the bearing maintenance they have to do. That they have done that. Now it is working good. So I want to show the reports. Just wait, please. Oh, sorry. That is, I have given it in railways. I will show that report. It will be of useful. That is in railway. So this is the condition assessment care from bridge, which we have done. This is July 19 we have done. So these are the letters they have given. Yeah, this is our team. And these are the components of different locations. The vibrational analysis which we have done. Yeah, these are the vibration measurements we have done. Yeah, that is the close-up view. And these are the different vibrations for all the cables. We have done FFT analysis. And the bearing also, these are the bearing readings. The frequency is 2.3, amplitude is different amplitude. Yeah, these are the things we have given, the frequencies, and finally we have submitted this. So this was very useful for them, and they have now properly having the monitoring system. They are frequently asking us to complete this work. So I think this year also, because of pandemic, we are not able to go. Next year we are planning for 2021. We will be doing the same kind of a job. So then I will be giving you certain LabVIEW codings with regard to vibration. You see that this is the vibration project. So when you make that standalone system in the real time, if you want to make a measurement, this is called it as a project. We have to create a project. This will be automatically created when you are connecting the MyRio with your system, and it will configure there automatically. When you are opening the project to enable, it will be enabling. Then in that it will be showing main VI. In that VI you have to make your coding for acquiring the signal and as well as for further analysis. So this is the call it as a project. Okay, in any real-time work, if you want to do, we have to do through this way. What do you call this project mode? So then after that, in the same main VI, for example, so I'm just closing this. Here also I'm closing this. So I wanted to open this main VI. Yeah, now I have got it. You see that the project structure is like this. So like your state machine, which we have seen, for the state machine is for different use, but the project is as like in the sequence structure. Inside you will be having while loop. So the initially that sequence structure, it is to initiate that for the error handling. It is initially it is 0. Then we have used that is shift register here. The shift register is automatically, if any error is there, it will be intimating. So when the error comes, then automatically here it will be making it off. Suppose you can stop, that time also your coding running will be stopped, or otherwise if any error is happened, also it will be getting stopped. So this is the input channel. So here in the accelerometer, x-axis, y-axis, and z-axis something. For example, if you wanted to make see, you have to double click and it will go. You have to make a double click, and after that in the double click there you have to configure your channels. X channel 1, channel 2, what is the pin number, and so on. Like this it will come. Okay, so initially I have made pin number 3, that is channel A10, then A11 and A12. This is the channels customized. So that I have used for x-axis, y-axis, and z-axis. Okay, yeah. So here in accelerometer, I wanted to show this accelerometer how it is looks like. Sorry, that MI Rio, how it is looks like. Just a minute, I'll be going for again. You are seeing here the accelerometer is here, correct? In the accelerometer, these are this side, the general configuration of Rio, my Rio. So this is the data connection and power connection. And here this is as like DAC, we can use it. And one more thing, we have input and output for voice recording. And this side we have A and B, all channels we can use. So A particular channels, analog input channel, analog output channels are available, and B also we have analog input channel and analog output channel. Right now what we have done, for the A, so A compartment in which we have used the channels. So that is the one I told you there. Okay, so this is comes under A channel, A101112. So this is AI0, AI1, AI2. So in LabVIEW always starts from 0, not from 1. 1 means the second channel, 0 means first channel. Like that it will be there. So here A compartment and AI0, and A compartment AI1, AI2, like that. Okay, that is X, Y, Z. So what will happen when you are making running? So I am not connected my Rio, it has to embed, it has to deploy, and it will deploy and it will progress. Because since I don't have the hardware, so it is not progressing further. Okay, now whatever we are getting, this is actually from the accelerometer. So that I am directly giving for accelerometer reading here. So we will be getting the waveform. And after that I am taking here. So one more thing I want to tell you. Suppose if you wanted to use for analysis this waveform, further you can subject for the filters. So here also in between you can use point-to-point filters. Any kind of filters you can use, low pass or band pass or any other thing. Relevant filters you can add over here. So that, but after filtering the signal, you will get a original signal. So all these signals now in the form of array, I have taken it out and you have got a waveform graph also. This is acceleration and the waveform graph you have got. Okay, this is the one I have done here. So this is actually with the equipment. Now I can going to simulate for you. Okay, now I am taking it out. So I will be simulating. Okay, so what I am going to do, I will be giving you some random numbers. So this random numbers I am just connecting it. So the time wait second we have given is 10 millisecond. Okay, 10 milliseconds we have given wait value. So now let us see how our acceleration is, simulated acceleration we are getting. I'm sorry, this is equipment should be there, then only it will be coming as. But what I can do, I can directly, I can uh, make the same thing without the projects. Okay. So I'm closing the project. So I can use a sequence. So this is a sequence structure. Add after. Again I can add after. So these are the typical the project diagram. Okay. So here we will be initiating and it will be closing. That will be there. And here what I can do, I have to use my while loop. So I am using my while loop here. So here what I can do, I can make okay, I can adjust. So now I'll be using my random numbers. This is the random numbers. Okay. Now what I can do, I can make a bundling. This is 1, 2, then it is. Then the front panel I'll be opening the graph. So graph I'm using the waveform graph. So this is the one waveform graph. So I'm connecting to the waveform graph. So now still it is in gray color, your coding is not fulfilled. That means here whether we have to give any condition or not. So I am making a condition of stop button. Now it is become white. Okay, this is my, otherwise while loop will continuously operate. Whenever we want, we have to off. On emergency here also you can make off, but I'm not doing that. So now what I can do, I can run the system. So what I can do, before that I will stop. So I wanted the wait time every 10 seconds, every 10 milliseconds. So I'll be giving every 10 milliseconds. So 10. Okay. Now I will be getting, yeah. So you can see that this the waveform is coming. The same way you will get the complete, okay, like this you will get X, Y, Z direction, the accelerometer readings, you will be getting it. After that, this reading can be utilized for making the analysis. So for that, I will be giving another VI. For example, this VI. You are seeing here. So the same thing from the equipment, now it is filtered. Okay, this is comes under which filter we can see. So this is equiripple low pass filter, point to point. Okay, so that will filter the noise and you will be getting only the signal. That signal you will be taking it as a accelerometer reading. So next, this is coming into further analysis here itself. So here we are making the analysis, the FFT analysis we are making here. So based on FFT, this is the first one which you are seeing is accelerometer reading. There are two accelerometers we have used. That's why you are getting so many colors. So each accelerometer, it is having 3 channels, which is X, Y, Z. Like the 2 accelerometer means we have got some 6. Okay. After that, these accelerometers now FFT analysis. Suppose if you are seeing here, the frequency ranges around 5.1. The frequency. This is FFT analysis result. Now this is the diagram. In that we can able to get, that is The fundamental frequency is 5.1. So like that, this is the coding for the frequency. See, for example, this is the file path. The file path which is connected there. This is the sub A actually. So here is the sub A. Here correspondingly, whatever the output is coming, it is coming to the file path. Okay, whatever output is coming, that is the file path. So now what I can do, for example, here this alone I can take, instead of file path, I have there I can directly give that, okay, give the value here. So this is this particular this thing. For example, for particular this thing, suppose if you have an accelerometer reading, that accelerometer reading, it will take up the data. And after that, this is going to analyze. So I will show you some of the data. So in real time, you can see, I will show you some of the data. In the care from bridge itself, we have got all the data. These are the cable number. So, for example, cable number 3. So, these are the accelerometer data, X, Y, Z, the 3 different accelerometer reading in terms of volts. So, this will be captured there. So, what I can do in that particular VI, so in this particular VI, I have to open. Here I am, for demo purpose I am making open. But actually, if it is a sub VI, automatically that will be taken from the main VI. So now I wanted to use the exactly D, and in that consultancy. So in that railway. So suppose cable number 3 or 4, whatever it may be, let us take cable number 6. So now it is done. If you make now, you can on the run button, then you will get it. I'll just seeing here. I think data is not there in that particular. I will go to some other thing. 3. You are seeing that now. In cable number 3, we have the data, accelerometer rate data. Now you are getting the fundamental frequency. The frequency range is 2.25 or something. This is the FFT analysis. See how the FFT analysis is done. So now this is the data. It is from the accelerometer. Then the accelerometer, it is segregated into, this is the 2D array. In the 2D array, we wanted each axis, one particular data is there. No, one array is there, array of data. So that we are segregating here. This is, we are splitting the data, that we are taking separately the thing. So, and after that, that I am taking here into, so the cumulative I am making here, automatically what it is going to have, each one I am going to append. So here the scan rates is given. Normally, generally I am giving either 50 or 100 scan rate I am using. Generally I am using 50 and we will get a good results. So under 3 channels, that's why 3 length, that much data is going over there. So these 2 things are append and we will be getting time waveform. So further the waveform, it is given to the Fourier transform and fast Fourier transform power spectrum. So here on that you will be getting the power spectrum diagram. Okay, and further also you can take out what is the fundamental frequency and that magnitude of everything we can calculate from here. So we have made the fundamental frequencies here, right? So this is the maximum fundamental frequencies in all x and y z axis. So this is the way all the cables have been properly made vibration analysis. Okay, my dear faculty, I think I have finished, and if you have any doubt, you can ask me now. Yeah, I'm stop sharing. Now this is the time for discussion. If anybody interested, we can have a discussion. Participants, you can ask your questions. Then only I can answer more. Yeah, please you can text me. Any doubt, please you can text me. Umayal madam, do you have any doubt? Ram Babu? Ram Babu?
Yes, sir.
I think this is the time for discussion.
Yes, sir.
I'm waiting for discussion.
Participants, please unmute your mic, and if you have any queries, you can ask.
Please, you can text me if you.
Yeah, you can text in the chat box also.
Any kind of vibration analysis we can do along with this equipment, is it, sir?
Yes, madam, definitely we can do that. The accelerometer is the same. So the accelerometer, suppose if you want to have the precise, there are different kinds of accelerometer is available. Chrysler's, they are supplying a good accelerometers we used to import from there. And those accelerometers for different purposes, that is depends upon data updating rate, madam. So, and also depends upon the G, how much G and all. That is what kind of application accordingly, we can select an accelerometer, that accelerometer can be used. Again, the accelerometer, we have a different type. I have used the capacitive type. Clear, madam?
Okay, thank you, sir.
Thank you. Any others? Main thing in the accelerometer you have to procure. The rest all the thing we can use. Yeah. Is there any? I think Mr. Bhupati has asked about feedback links, sir. I think Mr. Rambabu, any feedback link is there?
Sir, attendance link we have given, sir. Feedback link will be for the final session, sir.
Okay.
Finally, all those 6 days feedback will be taken.
Okay, nice, nice. So right now they can give in the chat box, right?
No, attendance link I have given, sir. If any queries, they can ask in the chat box, sir.
Okay, about my lecture, you can give your feedback by chat box. I mean, in your chat link, there you can give your feedback about my lecture. Shall you please give 1 or 2 feedback, please?
Sir, thank you for giving the real-time presentation on vibration analysis, sir. It was very useful for us because going and seeing such things is very difficult. Now you have made it very easier to learn things. But only thing is we are unable to contribute much time for learning things.
Okay, madam, I do agree. So always offline we will be seeing real time. If it is offline, I might have taken you to the bridge actually.
Thank you, sir. Thank you very much.
I think if time permits, if any of the future workshops, we will be taking you to the real time bridges.
really it is very difficult to do such analysis in real time, isn't it, sir? You have done that.
But we have everything we standardized. That's why now it has become easy for us.
Okay. Okay.
We developed our own codings, and in the afternoon I am going to talk about all these things. We have now got some AICTE project and all, and that we are developing some new equipments. So that I am going to discuss in the afternoon.
Thank you, sir.
Thank you, madam. Thank you so much. Thank you, sir. I think you people have given a very good feedback, very informative session. Mrs. Sabita has given. Thank you so much. I think all other people, I think you got some understanding. You are taking some learning through my presentation. I am very happy for that. Thank you for nice cooperation. Thank you so much.
Thank you, sir.
Thank
Thank
you.
you to your participants. We'll break for lunch now. You can join back at 2 o'clock for the third session of today. Thank you.
Thank you, Rambabu. Thank you.
Thank you, sir.